Hi guys, welcome back. Day 2 of learning. So looking at that worksheet, we first need to understand what a metal versus a non-metal is. The dynamic periodic table that I had in Canvas, or I have up in Canvas, you can kind of hover over these different things and it'll separate depending on what you're highlighting. So we have our alkali metals, alkaline earth metals, our transition metals are going to be here in like a weird salmon color. Then we have our noble gases at the far right end and the other metals. Our metalloids are going to be this kind of greenish color, that staircase. And remember, the metalloids act both like metals and nonmetals. So they're separating our metals and our nonmetals. So to the left of the metalloids, those are our metals. To the right are nonmetals. So if we're looking at this, we have boron, silicon, uranium. These guys are all going to be the ones that are our metalloids. So to the right of that, it's a different color. All of these ones are metals. And on the other side, these are all our non-metals. And there's one annoying one that is also a nonmetal, and that is going to be our hydrogen. Hydrogen is actually a nonmetal. So think like if we could cut it out and paste it right here, hydrogen would fit perfectly next to helium. But it's located on the left side of the periodic table because it has a lot of properties that are similar to the alkali metals. So that's why it's located over there. Cool. So when we get to the worksheet, it's asking us to look at our metals versus our nonmetals. So it says highlight the metals in red and the nonmetals in blue. So really all you have to do is you have to go back to the periodic table, and we have lithium as our first one that we're looking at. Lithium is located right here. So it is in the metal side, so you would highlight that in red. So highlight that one in red. So you're going to go through the whole worksheet, or this section, I guess, and figure out which ones are going to be red, metals, and which ones are going to be blue, nonmetals. The question underneath it asks, which side of the periodic table are metals located? Well, we just said that. The metals are located on the left side of the periodic table, where the nonmetals are located on the right side of the periodic table. Next question. So I guess, can I edit this one? No, okay. What section of the periodic table separates the metals and the nonmetals? Well, I just said that. It's our green ones highlighted here. So those are the metalloids. The metalloids, and we had that in here, that's how you spell it. The metalloids separate our metals and our nonmetals. Okay, that's my dog Lily. She's wild. Okay, next question. Determining charge of an element, highlight the correct answer below. So do metals form a plus or a minus charge, and what are they called? And then same thing for nonmetals. So let's look back over here. So we know our metals are on the left and our nonmetals are on the right. Let me get rid of all of this writing really quickly. And let's talk about how we determine when elements have a charge. So if we are drawing the Bohr model, let's just do lithium. So lithium, remember 1, 2, it's in the second row. So that means it has, if we're doing the Bohr model, it has 2 shells. Remember the first shell holds 2 electrons and the next shell can hold 8 electrons. But since lithium is in the first column, it has 1 electron. All of these alkali metals have 1 electron in its outermost shell. So 1 valence electron. So lithium has 1 valence electron. Now remember, all of the elements, they want to look like our noble gases. These guys over here. Wow. Look at those beautiful noble gases. They all want to look like the noble gases. So they can either gain electrons to have a full outer shell, or lose electrons to have a full outer shell. So if we were looking at helium, it is in the first row. So it has one shell, and helium's a weird one. It has a full outer shell, but remember that first shell only has 2 electrons. If we're looking at neon, it's in the second row, so it has 2 shells. First shell is full, and the outer shell is filled, and it has 8 electrons. Can you hear that music? It's my neighbors. They like to jam out. Okay, so lithium either can gain 7 electrons to look like neon or lose 1 electron to look like helium. So what's easier? Well, it's going to be easier for lithium to lose that 1 electron and drop into that inner shell to look like helium. So let's do that. No, how do I just erase a little bit? Oh, frick. Okay, I'm going to redraw. Bam, it dropped in. So now it just looks like that. So now it looks like hydrogen. Alexa, off. Okay, so lithium will drop that outer shell and will look like helium now. So lithium's proton number is 3, so that means it has 3 positives on the inside, 3 protons. And remember that these little dots are the electrons. The electrons are negatively charged. So initially, lithium had 3 electrons, 2 in the inner shell, 1 in the outer shell, but we lost one of those electrons. So one of those electrons went away. So now we have 2 negatives and 3 positives. So we overall are positively charged by 1. Positively charged by 1. So lithium, its charge, and actually all of the alkali metals will end up with a +1 charge. Our next column over, they will all end up with a +2 charge. So if we look at beryllium, it has a full inner shell, and it's in the second row, just like lithium, so it has 2 shells. But this shell has 2 electrons in it. Now, beryllium can gain 6 electrons to look like neon, or can lose those 2 electrons to look like helium. It's easier to lose, so when it gets rid of those 2 electrons, and again, it has a 4+ charge inside, it will become positively charged by 2. The transition metals have weird rules, and actually in this unit, we are going to learn all about the transition metals, but we're just going to kind of ignore those for now. So ignoring the transition metals for now. When we get over to our next column, we have our group 3. So see how it says like 3A right there? 3A, so that's really what you're going to look at. So these form a 3+ charge. Our next column, they form a +/-4 charge. Kind of, we'll talk about that in a bit. Our next one would form a -3 charge. Now let's talk about nitrogen. So nitrogen has 2 orbitals. First one is filled. The second one, it's in the 5th column. So it has 5 valence electrons in that outer shell. Now, it either would have to lose 5 of its valence electrons to drop into that inner shell to look like helium, or it could gain, right here, 1, 2, 3. So that's what it's going to do. It's going to gain 3 electrons. Now, it does this by sharing electrons or taking them, but mostly sharing. Anyways, so when it gains those 3 electrons, nitrogen has 7+, right? And when it's neutral, it has 7-. But when it gains 3 more, now it's going to be overall heavier on -3. So that's where its charge comes from. So that's where that -3 charge comes from, because it's gaining those 3 negative electrons, making it unbalanced, right? So the 7 initial positives and the 7 initial negatives cancel each other out to be a neutral atom. But when we gain those 3 negatives, that's when it becomes a charged ion. Okay, our next column, our group 6, our oxygen group, those will form a -2, gaining 2 electrons. And then our halogen group is going to be -1. They just need to gain 1 more to look like those noble gases. The noble gases will not have a charge, right? They're already perfect. Everybody wants to look like them. They have that full outer shell, and that makes them super, super stable. And that's why everybody wants to be like them. So they won't gain or lose electrons. So there might be a few trick questions in your worksheet saying like, oh, who would neon form a bond with, or what would its charge be? And it wouldn't form a bond. It's not going to form a bond. Okay, cool. So let's go back to this worksheet. So it says metals form A, and if we go back over here, these are all of our metals right here. And again, this is like separating it. So like aluminum is a 3+. So they all are forming plus, right? So it's forming a plus charge. And remember we said that we have 2 different types of ions. We have cations and we have anions. Remember, cations, cats have pause, and pause means positively charged. So metals will form cations, a positive charged ion. Where nonmetals, they are, let's go back here. We have our anions here, negative, negative, negative. Anions are going to be negatively charged, and they form a anion. Remember, an anion, it won't let me edit on that page. We said a negative ion, which that whole thing is an anion. Cool. All right, so then it says write the charge and charge number next to each element listed. For example, beryllium is a 2+. So if we go back to this page, I'm going to get rid of all of this stuff really quickly. So beryllium is located right here. Again, it's in the second row, second column. Really, the second column is the important part. That's telling me that it's going to form a 2, either gaining 2 or losing 2. But since it's a metal, I know it's a +2. A+2. Same with magnesium, same with calcium. All of this whole row, they're all going to form a 2+ charge to become stable. So that's what that example is saying. So for lithium, it is in that first column, the first column. So it's going to form that 1+ charge. So fill all those out. I'll have the answers up in a minute. Then you can check them all. Okay, so covalent bonds are between. Think we're co-parenting 2 parents of the same. Covalent. Oh, that's so ugly. Hold on, let me redo that. Covalent is between 2 non-metals. So again, hydrogen is a part of this. Woohoo. And then these guys. So the purple, inside the purple, any of those ones. So we could have carbon and hydrogen, right? And that would be a covalent bond. H2O is a covalent bond. CO2 is a covalent bond. Those are all examples of covalent bonds because it's between at least two nonmetals. So the compound is only made up of nonmetals. Cool. The other question was asking about ionic bonds. Ionic bonds are between ions. Remember, an ion is a charged particle. When do particles become charged? By fully losing or fully gaining electrons. Covalent share. their electrons, where ionics are attracted based off of their opposite electrostatic attraction to each other due to fully positive and fully negative. So all of our metals, remember, will form a plus something charge, and our nonmetals will form, so all of these guys over here will form a negative charge. So when you have a metal and non-metal, that's when they will form an ionic bond. Cool. So again, you could have like sodium, NaF, right, and fluorine. That's an ionic bond. Sodium is a metal and fluorine is a nonmetal. They both form ions, and that's why they're attracted to each other. Okay, sweet. So again, covalent bonds between two nonmetals, at least two nonmetals, and then ionic bonds are going to be between metals and nonmetals. So then it's going through and highlighting the compounds in pink, the ionic compounds in pink, and covalents in yellow. So for this one, really all you have to do, and the metals are always listed first in a compound. So look at the first element and say, hey, is it a metal or is it a nonmetal? If it's a metal, then you know it's ionic, so you would highlight that in pink. So for oxygen, well, I know that's a nonmetal, so that's going to be yellow. Calcium is in the second column, and that's an alkaline earth metal. So this compound would be ionic because I know calcium's a metal, right? So you're going to go through each one and try to figure out, is it a metal or a non-metal? People always get tripped up on aluminum because it's in a weird spot on the periodic table. It's right here. You know that aluminum is a type of foil, a metal foil. So don't get tripped up by it. You know that aluminum is a foil. It is aluminum foil, what you barbecue and whatever with. That is the same aluminum in your house. So that is a metal. Okay. So then we get down to writing the correct formula for each compound. I'm going to show you a trick or remind you of the trick for ionics. So let me erase this again, and we'll just do the first one together. This is the first one. So we have sodium and chlorine. So Na and Cl. So sodium is in that first column. So sodium is going to form a +1 charge. Chlorine is in the column right next to the noble gases. So these guys are going to form a -1 charge. They are equivalent. Their charges are equal to each other. So for every one, and you kind of do like this crisscross thing. So for every 1 sodium, I'm going to need 1 chlorine for everyone to be happy. So when we write this, I need 1 sodium. Remember, the metal goes first for every 1 chlorine. And that's it. That's your chemical formula right there. Let's do a harder one. Let's look at, let's do magnesium. Let me do it on the right side. And chlorine. So magnesium is in that second column. So this whole column, they all form a +2 charge, right? And chlorine, we just talked about chlorine, has a -1 charge. Now again, we do this crisscross thing. So for every 1 magnesium, I need 2 chlorines. So when I write this, I need 1 magnesium. So I won't put a subscript because I just need 1. And for every 1 magnesium, I'll need 2 chlorines. The 2 subscript, again, tells me I have 2 chlorines. When there's not a subscript, that means that we just have that element, one of those elements. You could draw the Lewis dot structure to show how these are chemically bonding to each other and why we specifically need 2 chlorines. Let's do that really fast just to make sure we understand. So magnesium, or Lewis dot structure, has 2 valence electrons, and chlorine has 7 valence electrons, right? So magnesium can donate its 1 electron to this chlorine. The chlorine becomes happy. It's like, I look like argon, I'm so cool. But the magnesium's not happy because the magnesium still has that 1 valence electron. So another chlorine needs to come in and help the homie out. So that chlorine comes in, stay consistent with these colors, and it will donate that electron to the chlorine. The chlorine is happy. The magnesium will drop down into its other shell, the lower shell that's full. So it looks like neon, and it will be happy too. So now everybody's happy. When we look at it, we have 1 magnesium, right? And we have 2 chlorines. So when we write that into a chemical formula, again, the metal goes first, 1 magnesium, 2 chlorine. So that's where we get that chemical formula from. Cool. All right, let's talk about one more kind of tricky one. So if we have magnesium and let's say oxygen. We already talked about magnesium has a 2+ charge. Oxygen, it is 1, 2 away from looking like a noble gas. So these guys will have a 2+, or sorry, that's right, a 2- charge. You could say -2 and +2. It doesn't really matter as long as you know what the charge is. So cool. So this is saying that for every 2 magnesiums, I need 2 oxygens. But because they're both even numbers, they can reduce down. So really, actually, I just need 1 magnesium for 1 oxygen. And we can draw this out to make sense of it. So magnesium, again, we said has 2 valence electrons. Oxygen has 6 valence electrons. So this one will get donated to that spot. That one's going to get donated to that spot. And you can see right there, oh, everybody's happy. Magnesium's happy. Oxygen's happy. They all look like noble gases. And I just have 1 magnesium to 1 oxygen, right? So we can reduce these down to a 1-to-1. And if it was like let's say it was like 2+ to a 4 minus, you could reduce that down to a 1-to-2. And then that would be like, I need 2 of those and 1 of those. Hopefully that makes sense. So when we go back to the worksheet, what I would do, and again, it's not letting me edit on this worksheet, I would write above each of the elements. So like, oh, sodium has a +1, chlorine has a -1, so I need 1 sodium, 1 chlorine, and then it's just NaCl. Hopefully that makes sense. For this worksheet, it looks like we had a few examples of our covalents. So again, if it's a covalent, it's going to be a little bit different because covalents aren't totally donating electrons and totally accepting. They're sharing electrons. So let's look at that. So one of them was C and O. So when we're looking at this, again, for these examples, you're going to want to draw out those Lewis dot structures. Remember that in our last unit, we talked about VSEPR, and it was the 3D model. So these electrons aren't held in those spots per se. So like we're going to form a bond between here. Oh, that's weird. Hold on. Okay, between here, boop, boop, boop. And then this electron is actually going to migrate over to this side, and this one will migrate over here as well, and we'll have a double bond right there. So our oxygen's happy. Again, this goes away, and I don't know why I can't just like, oh, I can. Look at me go. Okay, so the oxygen is happy because, again, it has 1, 2, 3, 4, 5, 6, and it's sharing these 2, 7, 8. So it's happy. It has a full 8 outer shell, but the carbon isn't. So it's sharing these 4, 5, 6, but it still needs 2 more to be happy. So we'll have another oxygen come into play. And again, we'll show, oops, there's one right there. We'll show the bond between these two, and then this one's going to migrate over to here, and that one's going to migrate over to there, and you'll have that bond right there. Look at me with a fancy eraser going. Okay, so now everybody's happy. Carbon's happy, oxygen's, oh my gosh, happy. So it has 2, 4, 6, and it's sharing these 2, so 8. Oxygen has 8, and then carbon has 4 here and 4 here, so it also has 8. So for this example, our formula is going to be 1 carbon and 2 oxygens. And you might be like, well, why did you do carbon first? Carbon is located further left on the periodic table, so it's written first. Cool? All right, so after you watch this video, I'll have this answer key up there for you guys to see as well. And then you can run through those. If you have questions, let me know. And that's that. Hopefully this makes sense. You guys will have a new worksheet. Actually, we're going to go through some notes tomorrow. I'll do a video on it, and then I'll go through some example problems on restarting nomenclature. So naming ionic binary compounds, the rules that are involved with that. It's really not that difficult, but every day we're going to be adding new rules. Again, remember the first worksheet here, I said polyatomics have different rules, transition metals have different rules, and then covalents have different rules when we're naming these compounds. So when we get into that, things are going to get a little bit wild. All right, love you guys so much. I will talk to you tomorrow.